Very good. Okay, so we're a couple of minutes past. There will probably be a few more people who come along. But for now, we're extremely happy to have Steve James here. So Steve is a senior lecturer at WITS, co-PI at the Rail Lab. I'm sure many of you know Benjamin Rossman, but yeah, Steve is one of the other big players there, who got his PhD at WITS as well. Was it in the Rail Lab itself?
Yeah, it was.
Yep. Yep. And is going to tell us today about concurrent and temporal composition for zero-shot transfer in RL. Please, over to you.
Great. Thanks very much. Thanks, John. And thanks for the invite. I'm very excited to be able to be here to talk about some of the work we've been doing over the past few years. This is obviously not just my own work, but a collaboration with many other fantastic students. And I'll mention them at the end. I'm really just the messenger here, passing along some of the interesting work. Well, I hope you'll find interesting that we've done in the last few years. Okay, so let's jump straight into things. The kind of motivation for all of this work is if we're thinking about reinforcement learning and intelligence agents acting in the real world, the kind of target that we're looking at is the kind of final goal, which is, multi-purpose robots, agents that are capable of doing many, many different things. So as you all know, lots of recent success in reinforcement learning over the past few years, things like, AlphaGo, playing chess, all of these things, playing video games, fantastic achievements, very hard tasks that have been solved with reinforcement learning, plus, deep learning and a whole bunch of other things. And while those are all fantastic, kind of the key thing that's missing is it's all well and good to have an agent that can play Go at a superhuman level, but not so great if that's the only thing it can ever hope to do. And so what we're really after, if we're hoping to have real robots interacting in the real world, helping people going about their day-to-day lives, is having a single agent capable of doing not one thing at a superhuman level, but many, many different things, as many tasks as a human can do. So just like a human can, go and make breakfast and also drive a car and also play chess, we would hope that our agents have the ability to do all of these things. So the first thing that we're looking for is this idea of flexibility, to say we want agents capable of achieving and solving many, many different tasks in the world, not just one task very narrowly. This is what we would expect of a generally intelligent agent. Okay, the next kind of thing on our list that we would like of these agents is the ability to instruct them. So this is to say, okay, imagine again, we have robots in the real world, and humans interacting with those robots. We want to be able to task those robots to tell them, this is what I want you to do. For instance, in this picture, I want you to go off and make breakfast. And I should specify exactly what that breakfast should consist of, etc., etc. But I need some way of communicating my goals, my intentions to the robot. And now this is not a straightforward thing. Language is very ambiguous. We've seen a lot of research recently about, alignment and ensuring that the goals that we desire are in fact, the things that are communicated to agents in different ways. But ultimately, we need some way of instructing agents that they can go off and do the tasks that we care about. And the final thing related to this is the idea of reliability. So this is to say, okay, well, once we've gone off and told the robot this is what we want it to do, we should hopefully have, some confidence, some guarantees that come with that to say, if I've told it to go do this thing, it will in fact go do this thing. And it will do it in maybe a safe way or some predictable way. But we need this kind of badge of that we can verify that the behavior will be fine, because we can't have robots running around doing things that might be unsafe or doing things that don't exactly follow what we had intended for it to do. So these are kind of the three main components, three main characteristics that we're looking for in our agents. And what I hope to convince you over the next little while is that the kind of ideas we've been playing around with and the framework that we're working on kind of hits all of these points. Okay. So that is kind of the space we're playing in. And to start off with, I want to discuss three challenges. So the first challenge in reinforcement learning, I'm sure many of you have used reinforcement learning before, but you'll know that learning is very slow. Right? So if you're doing reinforcement learning naively and you want an agent to solve many, many tasks, well, then what you would have to do is you'd say, okay, well, the agent is around, and then I give it the first task, and then it goes off and it takes many, many samples, and then it solves that task. and then great, it solved one task, but now I needed to do another task. So now it has to go off and solve that task, and it takes many, many samples, and then it solved 2 tasks, and so on and so forth. And of course, this is, ignoring issues like catastrophic forgetting and all the other things that come with this. But that's what we might do in the most naive sense. But we know obviously that sample efficiency in reinforcement learning is just terrible. Like if you're playing a video game, it might be feasible to collect 8 million samples from the video game to learn how to play Pong, but that's not ever going to work in the real world. If you have real life robots, you can't collect 8 million samples, because by then the battery will long since be dead, the motor will long since be, destroyed. The amount of time it will take to collect 8 million samples, because you're operating in the real world and can't fast forward time, these things are just not feasible to run in the real world. So we have to somehow get rid of this problem of sample efficiency, inferior sample efficiency in RL, I should say. So we need to do this, and we need to be able to, tackle multiple tasks. And obviously, this is not a new problem. People have been thinking about this for decades and decades. There's lots of great work on things like transfer learning. But it's worth just mentioning that we kind of need transfer learning, because if we're looking at a single agent solving multiple tasks, we can't expect it to do one task after another. And, we need some way of transferring the knowledge, saying, oh, the agent has, solved or been trained on N previous tasks. If you get the N plus 1th task, well, it should be able to reuse some of that knowledge, at least in part, to accelerate things so that you don't have to relearn from scratch, and you can actually do real learning in the real world. Okay, so this is what we want. This is, again, a known thing. There's nothing new here, but this is kind of one challenge that we want to overcome. All right, the second challenge, which is maybe not as obvious as that first one, is that actually specifying the task is hard, especially in the context of reinforcement learning, which many of you will know. The way you define tasks is through a reward function. You say the agent exists in an environment. You want it to do a particular thing, like, oh, I want the agent to be good at playing chess. So you say, I'm going to define my reward function that says, well, when the agent wins the game, they get a +1 or +10. And when the agent loses, they get a -1. And then they should use that signal to kind of learn that, oh, the thing I should do is play chess well, so I can get lots and lots of reward. Okay, so this is how we define tasks, through these reward functions that output a scalar value. And you'll also know, if you've gone off and implemented these things, that it is often very, very hard to get a good reward function that, elicits the behavior that you want. You often need lots of expert knowledge to build this reward function. You have to play around with the exact numbers, so that, when the agent goes and optimizes and does all the stuff and optimizes its returns, it actually produces the behavior that you want. We know that if you misspecify the reward function, or you overlook a particular thing, the agent will do reward hacking, where it will accumulate reward by not doing the thing that you had wanted it to do, by doing something else. There are all these kinds of sci-fi thoughts experiments about paperclip optimizers and all the rest of that. But needless to say, it's just in general very hard to define a task. Okay, it requires an expert knowledge. And obviously, if we want autonomous agents, it's not feasible to say that, well, if we want the agent to go and solve multiple tasks, we need a human to sit down and define the reward function for every single task. That's far too burdensome for a human to do, and it's just not going to scale. So it would be nice if there was some way of defining the task symbolically. We can then communicate that to the agent through some kind of symbolic method, natural languages, formal languages, whatever the case is. We define it symbolically, and then this is how we specify tasks to our agent. Okay, so that's challenge number 2. And challenge number 3 is really just that reinforcement learning is really hard. Okay, so even putting aside the idea of specifying tasks or multitask learning, even if it's just a single task that you're trying to solve, that's just a really hard problem in general. For, we have algorithms that can do it, but, depending on how hard the problem is, it can, it can take a very long time, can take years and years of research to solve it, just a single task. So, especially in the case where you have a task where you require hundreds and hundreds of actions, and you have very little signal, very little reward coming back, that's a really tough problem to solve. So solving the task in the first place is really hard. There's a little animation here where the agent has to run around, open doors, collect the key to unlock the door, to get the treasure, and then go all the way back. And it's taking 1,000 actions to do this. And you can imagine if you got a reward signal of 1 at the end, that's going to be very hard to learn from. And then having, let's say we go off and we actually solve the problem. is there some way of providing a guarantee about the eventual solution? So we say, okay, well, I've come up with this clever way of solving a problem. Is that solution actually, safe? Can I verify that it's doing the thing that I wanted it to do? Can we provide some, guarantees about that? Okay, so this is the third challenge. Can we guarantee that the agent will behave appropriately, will behave safely once it has learned how to solve the task? Okay, so this is kind of the three challenges we want to overcome. And basically, if I'm going to summarize things, what we want is we want to be able to specify a task to an agent, to a robot, and something that a human can write down or speak. So for instance, we would want to say something like, I want you to go off and, do X and Y at the same time, or do X until something happens. And then once that thing happens, then you should do Y. And we'd want to be able to do this such that the agent doesn't have to start off from scratch every time, can reuse all of its previous knowledge, and then it can learn how to, achieve the task that we want very quickly. And then finally, we want to be sure that the behavior will be safe, guarantees around the behavior for whatever task we specify. So these are kind of the three things, addressing those three challenges that we want. Okay, so I'm sure everyone here knows about reinforcement learning. This is just a one slide summary of that, just with the main points that I want to hit on. Reinforcement learning, as you all know, there's an agent, interacts with the world, takes an action, gets back an observation, which is about the state of the world, and some reward for having taken that action in a particular state, and does this in a loop. And it acts according to its policy power. And so, sorry, I'm being maybe a bit obvious here, but it will come up a bit later while I'm specifying this. So power is a function of states and actions. It says at a given state, what's the probability that I take some action? We also have our value functions, which characterize how good a policy is. And this is basically the expected sum of rewards that we get from executing that policy from a particular state and just, rolling that out. And then the thing we're after is the optimal policy power star, which is just the best such policy over the space of all policies, the one that achieves the highest expected return from that. Okay, and power star over here, again, function of states and actions, represents the solution to a single task. So this is the standard reinforcement learning setup that we're all pretty comfortable with. And now I'm going to move away from this, but we'll see later why I brought this up. Okay, so jumping into things, the first question is, well, let's think about how we can specify complex tasks. I've said compound just because complex would imply that they're very complicated. We'll see some very complicated tasks later on. I'm just going to say compound for now, just to differentiate those two things. Okay, so let's say for argument's sake, we have two tasks, A and B. The tasks are obviously specified by Markov decision processes, but let's say there are two tasks, A and B, and they obviously have corresponding reward functions, A and B, and those reward functions, tell the agent how to solve the task. Okay, so we can think about, okay, let's say we've got A and B. What is a useful way, or maybe an intuitive way of combining these two tasks? And the first thing you might think about is like way back when you started computer science and you were in first year and you were in the very first module, and you learned all about how computers work, and there were logic gates and all the rest of that, and you probably learned something about Boolean truth tables. And this was saying, okay, well, here's how computers can do, logical operations on things. And we basically saw a table that looked like this, that said, oh, well, if your inputs are zeros and ones, and zero could mean false and one could mean true, then you can compute like the OR of two things, like A or B. Well, it's one if at least one of them is a one, and it's zero everywhere else. And similarly, if you wanted to do A and B, well, it's zero all the time unless both A and B are ones, both of them are true, then A and B is true. And we could do things like a not, and a not we just kind of like invert it. If A was a zero, then A becomes a one. If A is a one, A becomes a zero. So this is kind of what we learned back in first year computer science. We have a Boolean truth table like this, so we could think, okay, well, what if we could do the same kind of thing with tasks, right? Like if A and B are no longer just Boolean variables or binary or bits, what if they were now tasks? What if we were talking about A as a task and B as a task? Can we do the same kind of thing? Can we do ORs and ANDs and NOTs over these tasks? Okay, so that might look something like this. So doing A or B, like task A or task B, you could imagine this is something like, imagine I said to the robot, I want you to make me breakfast. and it should be toast, but the toast could be white bread or brown bread. I don't have a preference, either or will do. So we could say task A or task B. And what you'll notice from this Boolean table over here is that if you want to calculate the OR, you just take the max over A and B. So whenever there's a 1, the max of 0 and 1 will always be 1. And when it's a 0, it will be 0. So to compute the OR, it's a max. Similarly, to compute the AND over here, it's actually a min. Just take the minimum number and you get the min. And then to compute the NOT, it's 1 minus whatever A was. Okay, so it turns out that under certain conditions, which I'll briefly mention in a second, under certain conditions, we can actually do the same thing. We can say the task that semantically means A or B is just the task that has a reward function where you take the maximum over the reward functions for A and B. And similarly, the task that means do A and B at the same time, the conjunction, is just the same task whose reward function is the minimum of the reward functions of A and B. And then if we want to do not A, so if we want to take like the negation of a task, we kind of do this thing where we say 1 minus the reward function, except this 1 is more like a constant term that, you know, depends on other things that I won't mention here, but it's just some constant number, but you can think of it as like a 1. So you say 1 minus the reward function, and you get a task that is basically don't do A. It's the negation of A.
Can I ask a quick question here?
Sorry, yes.
So here we're thinking about, so you've written here as 2 MDPs, A and B, but in some sense, is it right that the state space of the two has to be the same?
Yes.
And correct. We're just defining different reward functions over that state space?
Absolutely. Yeah,
okay.
That's right. So to be clear, and I'll mention this now with the reward function, so tasks are related in that they have the same states, same actions, same everything. The only difference is how we're treating the rewards. So we can think of tasks as like, this is the environment, this is how the dynamics work. It's all the same. And then the rewards specify, okay, what must I go do in this environment? And so what we need is that A and B share all things the same. And the reward function, there are a few like ways of like, we can define different kinds of assumptions, and the more stricter we get, the more we, you know, there's trade-offs that we can make. The most strict version basically says we need that A and B have the same rewards everywhere, except at goals that we might want to achieve. That's kind of like the strictest assumption that we make. So this means at all states where the agent is just, you know, doing some stuff, A and B must have the same reward function. But when you reach some goal, and maybe that goal is like, I'm an agent and I'm walking around and I'm picking up objects. So a goal could be, if I pick up a particular object, then the rewards can differ, but only when I pick up the objects. Everywhere else, the rewards must be the same. So this is kind of the assumption we're making. And then this holds. So this Boolean algebra holds under these conditions and under some like weaker conditions, which I won't mention here, but this holds. And we can then say, okay, if I've got 2 tasks A and B, I can do the conjunction, the disjunction, and the negation of tasks by simply running these operators over the reward functions. Okay, cool. So that's great. We can now specify compound tasks using operators like or and not, which is useful because many people, you know, have an intuitive understanding of what it means to do or and or not. Cool. So the next question is, okay, but how do we actually go and solve these tasks? So the intuition here, what we're going to do is we're going to define a new kind of value function. It will be a general value function, but it will represent something very specific. And the intuition behind these value functions is that while we're learning how to solve one task, we should also learn things about solving other tasks that we're not supposed to solve now, but we should learn something about them in case in the future we might have to solve them. So this is the main idea here. Let's say we have 2 tasks A and B. If I'm trying to solve task A, while I'm doing that, I should maybe learn something about task B that I could use going forward. So this is the idea. We're making a single change, and what we're doing is we're introducing another dependency on the reward function and subsequently the policies and the value function. And this dependency is on G, which is a particular goal. And so what we're saying here is that our new reward function, which is now goal condition, says, if I enter some state S, and that S is an element of G, which we're going to assume that there are a bunch of goals that the agent can achieve. So I've entered some state S, which is a goal state, and S is not the goal G that I'm looking for. So again, let's say I'm an agent and I'm looking, my goal is to pick up blue things, and I've accidentally gone and picked up a red thing, because I'm trying to learn about the world. Then this would say, oh, you've entered a goal state, but it was the wrong one. You picked up a red thing. You were supposed to pick up a blue thing. That was the wrong thing to do. When this happens, we give it this penalty term, RMIN. And basically the idea behind RMIN is it's the largest penalty that you could ever hope to achieve in the environment. So it's just like a really big negative number, like minus 1,000 or minus 10,000. You can like theoretically show what this number should be. But basically the idea is just to say, this is the worst possible thing you could do. There's nothing worse you could do than achieving the wrong goal. So you should never achieve that. So we give it this penalty if it achieves the wrong goal. And then otherwise, for all other cases, it's just the standard reward function. So we're just augmenting this reward function with this one case that says, if you achieve the wrong goal, you get a terrible penalty. And that's it. That's the only change we make. And then everything else stays the same. So like the value functions can still be computed with standard reinforcement learning algorithms. You can still do Q-learning. You can still do value iteration, whatever you want. The Bellman equations still hold. It's all the same. You just have this kind of new value function, which we call a world value function for, just to give it something to call it. So we get this world value function, which is now conditioned on G as well. And then the policy, again, you can act greedily with respect to this. The policy, again, would be conditioned on G too. So we've introduced this G, modified the reward function slightly, and we get these new value functions and new policies. Okay, so this is the plan. And as I mentioned, the only difference is there's a penalty if we reach an unintended goal state. Otherwise, it's just the standard regular reward. Okay, so just as an example of what we actually end up learning, let's say we're this agent in this video game, and the task here is to collect blue objects. So you have to walk up to a blue object and pick it up. So blue objects are good to pick up, and all other objects are bad to pick up. You would get that big negative reward. So the value function that we end up learning, the goal condition value function, looks something like this. So we're learning like a stack where, each of these layers is like for a particular goal. And what you can see is that for cases where it's blue, then the values are very high. So value function for blue things is very high, like blue circle, blue square. And for all other objects that are not blue things, those values are very low because we got the big penalty for saying, oh, you picked up a purple circle. That was the wrong thing to do. So we've learned like the stack of value functions, this goal condition value function, and now we're going to do something with it. Okay, as an aside, before we move on, it's important to note that we can actually recover original policies. So like if we want to go back to standard reinforcement learning, which ultimately we want to do when we want to act, so we can recover that by simply maximizing over the goals. So we can take the max over that goal dimension. And if we do that, we go from something that looks like this to a value function that looks like this, which is in fact the value function for collecting blue objects. Okay, so we can just go back to standard RL. We have a pathway back by simply maximizing over goals. This is also nice because what we get out of this procedure here, once we've learned this, is we get this value function. And you'll know that it's actually quite hard to learn multimodal value functions in reinforcement learning, in particular because there's a tendency, if you learn a policy that goes to like the one blue item more than the other one, then there's a bias to keep visiting that same trajectory. And so you might learn the true value of going to this blue object and not quite the true value of going to this one, because there's this kind of winner takes all bias.
Sorry, can I ask another quick question here?
Yeah, sure.
You've written this as the action value function Q.
Yes.
How are you plotting that just as a function of the state space?
Yeah, so the way you generate this plot is basically it's Q, and then we basically move the agent to each cell in the grid, and then we look at like, okay, what is the best action to take? Because
so this is really V derived from Q.
Yeah, this is really V. Yeah,
okay.
Because it's hard to visualize Q, but yeah, this is really V. Cool. And the same holds for like if we had the same thing to learn like how to collect squares. Well, we'd get a goal condition value function that looks like this. Maximize over goals, we get something like this, and you can see there are local maxima over here and here and here, and this corresponds to going to collect squares. So the same thing happens here. Okay, so why did I mention all of this? I mentioned all of this because we said we had tasks, and we have rewards. And now we've done this, we said, okay, we can have a Boolean algebra over these MGPs under certain conditions. And now that we have these new kinds of value functions, A and B, we've learned one in A and one in B, it turns out that we get an algebra over the world value functions that are exactly the same as the Boolean algebra. There's this homomorphism between them. And so if we want to solve the task of doing A or B, we simply do the exact same thing. If we want an OR, we take the max over these two things. If we want an AND, we take the min. And if we want the negation, we take, again, some constant term minus the value function, and we get ORs and ANDs and NOTs. So this is great, because now if we just specify the task is A or B, and I know A and B separately, then I can solve this by simply taking the max. And similarly, if my task is do A and B at the same time, then I can simply take the min over the value functions, and so on and so forth. So I can solve these tasks zero shot, given A and B, by simply computing using these rules, these operators. Okay, so just to show you an example, if we took the min over two value functions for collecting blue things, for collecting squares, then we get something that looks like this. So we get this goal-oriented value function. Then to actually act, we maximize over goals. We recover the original value function in standard RL, and then we can act greedily with respect to this. And then you can see it learns, oh, we must collect the object that is both blue and a square, a blue square. And we can do the same thing for ORs. We take the max over blue and over squares. We get something that looks like this. So this will be, the maximum over all objects that are either squares or blue squares. So it's that one, this one, this one, and this one. And you can see those over here. And then we can do things like NOTs. So NOT says, give me things that are not squares. And so I get something that looks like this. So this is like, give me something that's not a square, and then it will do that for you. And it will, this one here says, okay, I'm going to go collect something that's not a square. And this one says, what's the thing that's not a square? And it takes you to that. Cool. And then obviously you can do more complicated things, because if we can do ands and ORs and NOTs, then we can do things like exclusive OR and NOR and NAND and all the rest of that. So we can do exclusive OR just as you would with a normal, Boolean expression. We get something that looks like this. And this allows us to have a policy that says, well, collect squares or collect blue things, but don't collect blue squares. And you can see the trajectories here show it will go to squares and blue things, but it won't collect the blue square. Okay, so this is great. And our theory gives us some reliability, because it says, oh, well, if we have optimal skills, optimal value functions A and B in this kind of these new goal-oriented value functions, then if I need to solve these compound tasks like ORs and ANDs and NOTs, then we have proof. Well, we have theory that guarantees that the resulting thing is optimal, and we don't need to do any further learning. We're just computing maxes and mins and subtracting things. So no further learning needs to take place. And so what that means is if we have tasks that are like, go to the left rooms here, so these red dots here specify the goal in like a 4 rooms domain. This one specifies the goals at the top rooms. Given these two things, we can do things like the OR of them, like go to the top or the left rooms. We can do the AND, go to the top left room. We can do the NOT of A, which says go to rooms that are not left. So that would be here. And we can do things like XOR over here, as we saw. And the important thing about all of this is that we've made a slight change to the value functions, but we can still bring to bear all of the different reinforcement learning algorithms to actually learn these. So regardless of how hard the task is, or if it's continuous states, continuous actions, whatever the case is, if a reinforcement learning algorithm exists to solve it, we can just deploy that. So like here's a continuous action space example. We have like a Majoko and maybe the first task says you must reach goals in either of the top rooms. So we run, in this case, I think a soft actor critic. We run it and it learns how to do this. And then we say, okay, well, that's great. Let's do another one where we go to the left 2 rooms and we visit the center of those rooms. So again, soft actor critic can just go and do this. And then having done that, we can then say, okay, well, that your learning is now done. If I wanted you to go to the top or the left rooms, then zero shot knows how to do this. You just take the max and it comes up with this policy. We can do top and left. So only go to the rooms that are both in the top and the left, so the top left room. And again, we get the policy for free. And we can do, again, like top exclusive or left. So either the top or the left, but not the top left. And again, zero shot behavior comes out of this. Sorry, yes, I see a hand.
Apologies, hi Stephen. Apologies, you already answered this, but a quick question is, how are you avoiding the bias? I know you spoke about it from the terms of like perspective of multimodal rewards, but like in terms of the or when you performing the combining the two policies, wouldn't it be biased from like if one policy has visited like the top room, left room more than the other one?
Sure, yeah, that's absolutely possible. So all our theory holds in like the optimal case. So assuming that we have optimal value functions for all of the different things, we then have theoretical guarantees that says the thing will definitely be optimal. We also actually have like bounded guarantees that say if there's like some suboptimality, this is the suboptimality that you can expect. But in general, like, you know, this is function approximation we're dealing with in the images here. And so nothing is ever going to be optimal, but things still actually in practice work out fairly well. So we're in general optimal, very close to optimal, even when we don't have those theoretical guarantees. But it very much does depend on how much you train. So in general, we need them to be pretty well trained, like going to the top, like going to the left, and going to the top needs to be pretty well trained in order for, you know, to be pretty close to optimal so that the resulting compositions can be close to optimal. So certainly in the function approximation sense, that's important to have. But yeah, thanks for the question. Cool. Okay. So we can do all of these things, which is great. And the nice thing here is that in general, because we can do all of these different Boolean compositions, we have like a Boolean expression. And if we have k tasks, that means we can have a Boolean expression over k terms. So in theory, what that means is that if we have 10 of these base skills, like 10 tasks we've trained over, then technically there would be 10 to the power of 308 different Boolean expressions and combinations that we could pick to then zero shot solve. Like we have all of that, we just write down that formula, we compute using max and mins and negations, and then we can solve that. So we get this massive scaling. Having solved 10 tasks, we can now, you know, solve basically an infinite number of tasks. Okay, so that's the idea. A final note on these kinds of value functions is that you might say, oh, well, you know, the value functions now are conditioned on the goal, so it's going to be hard to learn. It turns out actually that if you're just looking at like solving one task, like in this case, the task is go to either of the left two rooms. If we do like regular Q learning versus Q learning for our specific value functions, it turns out actually that learning our value functions is more sample efficient in the vanilla sense because we end up doing a lot of goal-directed exploration, which just outperforms epsilon greedy exploration. So yes, we have to learn more, but we can also reuse a lot of our data. We can do like hindsight experience replay, all the rest of that. And what happens in practice is that, yes, there's more to learn, but actually because of this goal-directed exploration, we actually end up learning faster, especially in the case where we have these multimodal goals, where we have these different goals and we need to learn about both of them. So not all is lost. We still learn relatively quickly, even though the value functions are now conditioned on a goal as well. Okay, but your mileage may vary there. Okay, cool. So we've done that. We've shown that, oh, we now have like lots of flexibility, and we also now have this kind of intuitive task definition. So I can say to the agent, go, give me blue things or squares, and it will do that. Or give me blue things and things that are also squares, and it can do that. And give me anything but not a square. I don't want a square, and it will do that. Right? So these are kind of intuitive ways of specifying things to agents, especially intuitive if you're, you know, a technically minded person. Okay, just to show you an example also, let me just turn off my pointer. So here's a video from some work we did on sim-to-real transfer in the same kind of setting. Again, this is about, you know, going to the left, going to the bottom. The main thing to talk about here is that, you know, we can encode the semantics of our different tasks, which means when we do ands and ors and nots, we can do ands and ors and nots over things that we want to be meaningful. So in this case, we have a left task, a bottom task, but we also have like a door task. And a door task would be going through a door, right? Because we specify, okay, going through a door might be a useful thing. I want you to go through a door. And then we can say, oh, well, I want you to go to the bottom and the left room, but don't go through the door because the door is closed. And then it will do that. It will not go through the door because we told it not to. But if we don't tell it, then it will, take the fastest route, which is going through the door. Here is like, go to the bottom and not the left and not the door. And so it will walk around all the way around because we've told it don't go through the door. And Kuru will be very happy to do that. Okay, cool. Another thing I want to quickly mention is that the kind of specific structure we give to the reward function, which I won't go into now, allows us to specify what we mean by ands and ors and nots. So we can almost select the semantics of what do we mean by the and of two tasks. And this is especially important. You can imagine you have two tasks that are very disjoint. What does it mean to do two tasks that are very disjoint? What does the intersection of disjoint tasks mean? That's a meaningless thing, really. So by specifying a particular reward structure, we can actually define what we mean. So in this case, we have a robot that has a red task, and the red task here means take all the red blocks and put it on like this green plank over here. So putting all the red blocks means we've solved the red task. And similarly for the blue one, putting all the blue objects on that blue plank means we've solved the blue task. Okay, so we go off and we train a robot to do this block stacking thing, can do red and blue. And then we can say, okay, well, we can do things like a nor. So nor means, neither the red nor the blue. And then that would, intuitively correspond to the case of, well, the not of the task means I should have nothing there. So now let's remove both of them because I wanted neither blue nor red. So now everything gets removed. In the bottom case over here, it says XOR, so it should be either blue or red, but not both. And because the blue starts off with a few more blocks than the red, the optimal thing to do here is to say, okay, well, I should just complete the blue. I should complete the blue row because it's only going to take me 5 blocks to stack compared to the red, which would be 7. And now talking about, defining the semantics of these different tasks, we can now think about, okay, well, what about the and, right? Because the and means like do blue and red, but there's no way to do it simultaneously. Either I would complete the blue first or I would complete the red first. So how do I do an and? So one way of doing it is just say, well, if the tasks are disjoint, then the and just means do nothing. Like we shouldn't do anything. Let's just not do anything and then we're done. But in this case, we can specify a particular reward structure where the and turns out to be do exactly half. Like the intersection means, do exactly half. And we can think of this as like, imagine I have one task that says go all the way to the left-hand side of a room. Another task that says go all the way to the right-hand side of a room. The intersection of that we then claim is go to the exact middle of the room. And we can enforce this meaning of and through the structure of our reward function that we gave for the individual tasks. Yes, Asad.
Sorry, just a very quick question again on like you touched on this, but like for example with the or, how is that did you observe that it reasoned when like you said that you found that they had less by the blues, so it did the blues first. So you'll just like observe like organically what it learns. Like it's not like randomly just choosing a red and a blue, or you found some pattern in how it decides when to choose red and when to choose blue.
Yeah, so remember, so these are like pre-trained, so we know how to do red things and blue things, so we know how to do all of that. So the nor, given that initial state, which is like over here, or maybe actually the XOR one is a better case, like the XOR one says, well, given this initial state, the optimal, which is, the fastest way to achieve it, given the reward functions, which would be like, -1 on every time step, the optimal thing to do to reach the goal fastest is just to complete the blue stack. So I'm going to do that because my base policies were optimal, so the composition is optimal, and the optimal thing to do here is just to complete the blue stack.
Thanks.
Cool. Yes, John.
Yeah, just thinking about it sort of semantically, I might imagine that the and composition for two tasks, if they're not sort of composable in the obvious way, would be to do them sequentially rather than to do the average of them. Can one think about that as well?
Yes, we absolutely can, and in a few slides we'll do just that. So hang on there, but yeah, that's a good point. Cool. Okay. Cool. And then a final note, just very briefly, I won't go into any detail here, is just to say, so far all I've spoken about is we tell the agent which tasks to learn, and then we give it a new task and we say, go off and do this task, and then it can do that. But also, if you care about the case where it's like a lifelong learning agent and there's no human around to tell it and it's just receiving tasks over time, what we show is, well, actually what you can do is you can go off and learn some tasks. The agent can be given tasks. And then if it gets in a new task, it can kind of work out, can I solve this new task by doing ands and ors and nots over my previous tasks? And if I can, then I should just do that, and then I don't have to do any learning. And if I can't, well, then I should learn how to do this task, save it in like my library of skills, and then repeat the process again. And we show that this actually works pretty well, regardless of the kind of distribution over tasks, even if it's like a very adversarially picked selection of tasks, or it's the best selection, or it's a random selection. At some point here, you can see, let me just get my highlighter out. At some point here, you can see that learning goes to 0. So basically, this means like for all future tasks after 40, no matter what the distribution we saw was, we can just solve those tasks 0 shot. We don't need to do any further learning. So that's great. We don't even need a human to sit down and tell us, you know, this task means A or B. It can work that out for itself. Okay, so this is all great, but it only works as long as the human understands what Boolean expressions mean, which is not always the case, especially for non-technical people. So we can think about, okay, well, how else could we communicate tasks? And the obvious thing is through natural language. And natural language is nice in the composition space because natural language itself, language is inherently compositional. Right? So if I have a sentence, well, I can swap out each part of that sentence for a different word meaning a different thing. I can swap out like a noun for a different kind of noun, and I can swap out a verb for a different kind of verb, and I can kind of mix and match these two things. And so language is inherently compositional here. And so what we can also do is we can kind of build a translation layer that says, given an English language sentence, convert it into this Boolean expression, and then given the Boolean expression, we can kind of run our previous framework, compose things, and solve a problem. And so we show in this work that you can do just that. Basically, how this works is the language model, the translation model, is trained to output Boolean expressions, and it gets a reward based on the agent going off and executing that expression in the real world. So it will say, it will output some Boolean expression, agent will compose according to those rules, it will act in the real world and get some return, and then that return will be used to train this translation model. That's the general idea there. Yes, John.
So can this then be trained end to end, or do you have to pre-train?
Yeah, that's a great question. So in theory, it can be trained end to end. In practice, we spent 6 months doing it with no luck. It turns out to be very, very hard to train it end to end. We got some success, but not much. It's just a very large engineering effort. We had hoped, yes, but in practice, you have to do each part individually as a pipeline. Cool. And then in more recent work, we show, oh, well, you know, everyone's using the large language models. It turns out that they're actually a better use case for this than the normal like T5 models. So we can use things like GPT-4, give it some in-context samples, and basically we say it translates the large language model, translates the text into some Boolean expression, it gets composed and evaluated, and if it's a success, then it gets stored as an example to feed back to the large language model to say, here's a good example that you should use as a prompt, and then we repeat this in a loop, and actually we do much better than the standard T5 translation models. Okay. Cool. So, and then as a result, what we can do is we can just say things, even in complicated environments, we can say, you know, go to the green chair, and then you could imagine swapping out green for like red and swapping out chair for sphere, and then it can do all of those things just from natural language. So this is kind of the start of this work of building a translation layer between natural language and these Boolean expressions. And again, it need not be in English. So, you know, for different languages, you could imagine building a translation layer for each of those languages to kind of make it more accessible. Okay, so the thing that's missing so far is we've done, you know, composition, which is great because we can specify different tasks and makes the agents very flexible. We can even translate natural language, but the things we can't do are these very difficult temporally extended tasks. So in this case here, for instance, you know, what we needed to do was collect the key, and then after collecting the key, unlock the door, and then get the treasure, and then do this, and then do this other thing, and we can't do that. Currently, all we can do is kind of solve one task, even if it's a compound task, and be done. But there's no notion of temporality going on. All right, so we want to be able to compose not just spatially, but also in time. So do things like first do task A and then B, or do A, but also never do this, and ensure that this thing is always true while doing this other task. And so in this case, linear temporal logic is a good candidate here. It has all these operators beyond ands and ors and nots. It has things like the next operator that says, after this thing, you should do this thing, or A until B, which is, do A until, B occurs, these kinds of things. So LTL seems like a good strategy to use here. And just as a work example, there's this domain called the office world, which is kind of used in standard LTL planning. The idea is you're wandering around this office. There are decorations that are these stars, and you should be careful not to knock over the decorations because then they'll break. There are rooms in the corners labeled A, B, C, D. There's an office with people in it. There's a coffee station and another coffee station. There's like a mail room where you can collect mail. And you could imagine we have tasks like deliver coffee to the office, but make sure you don't break any decorations. So tasks such as this. So if we were to write this down formally, the symbols are not important. It looks something like this. So this is like a formal language that says deliver coffee to the office and make sure that all the time no decorations are broken. And it turns out that you can translate an LTL sentence into a finite state machine or vice versa. You can go both ways. And so this finite state machine kind of gives you a high-level blueprint of how to solve the task. So it says, you start here, and then it says, well, if you break decoration, then you should just terminate. That was a bad thing to do. You get 0 and you should terminate. And then as long as you haven't got the coffee and the decorations aren't broken, then you should just stay in the state. And then as soon as you get the coffee and the decorations aren't broken, you should come down here. And then when you're here, as long as you haven't visited the office, you should just remain in this loop. And then as soon as you visit the office and you haven't broken the decoration, then you should terminate with a reward of 1. So this is telling a high-level plan of how to actually solve this task. And you can give this to the agent, and the agent can use this to accelerate its learning, as was done in this 2018 paper. Okay, so what we plan on doing here is we say, okay, well, if we're given the finite state machine, let's plan over the finite state machine. So let's treat this as like a little MDP. We do like value iteration, we plan over it. And then this tells us, if we act greedily with respect to it, this tells us like, how do we get to the goal? We act greedily, like we follow this edge, we come here, we follow this edge, then this edge, and then we stop. And each of these indicates, over here, it tells us how to get to this edge. It tells us we have to do this thing. So this is like the task that we have to solve when we're at this node. And you can see that this is a Boolean expression. So the idea is follow this thing greedily, follow the, here, the best thing to do is down here because you get 0.9. And then when you're here, the best thing to do is go down here because you get 1. So we follow this greedily, and at each node, the edge that we follow tells us what to solve, what task to solve, and that itself is a Boolean expression. And we just saw how to solve, things with Boolean expressions. So we can do this, and as a result, what we get is a policy that satisfies the LTL statement. It's not optimal; it's near optimal, and the reason it's not optimal is because we're acting greedily with respect to each node. Right, so for instance, in this case, this is the policy that gets learned, and it's not optimal because you start here and it says, okay, well, the first thing to do is get coffee, and the closest coffee from here is this one over here. And then once it gets this, it says, oh, now I must go to the office. But now we're over here, so to get to the office, we have to go all the way around. But if we had started here and then walked to the coffee station here slightly longer, then we'd be right by the office and we would just be done. So this is why we're not quite optimal, but we are satisfying. So we do satisfy the task. We did all the things we were supposed to do, but we're not optimal. And if you want optimality, well, you can use that policy and you can do like off-policy learning, and you can use that as a behavior policy and fine-tune it. And then we get the optimal policy that looks like this, where now you walk to the closer coffee, even though it's further away, and then you walk to the office, and we can deliver this. Cool. So this is the general idea. And because LTL just translates to finite state machines, and we can deal with that, and we can plan over that space, and we can do Boolean composition, we can do very hard tasks that are like this, which, R1 million, if anyone knows what this means. But yes, John, you want to take a shot?
No. But I was going to ask, can you use LLMs also to translate natural language into LTL?
So this is the future hope for our future work is we can hopefully go, this is very complicated sentences now. Can we go from this to that? And I'll talk a bit about it at the end, but I think the answer is yes. So this basically means deliver mail to the office until there's no mail left. Then once that's done, deliver coffee to the office as long as there are people in the office. And then when there are no more people in the office, then you should patrol the rooms A, B, C, D in that order, and you should never break a decoration while doing any of this. Okay, so we actually end up doing this. So we'll go and get the mail and deliver the mail to the people, and then there's no more mail, and then we deliver coffee, and then there's no more people. Now we patrol and avoid the decorations. And what you can see is that the total reward here, so we're optimal or close to optimal, and we're zero shot. So this is SM is ours, and QL SM is the fine tuning, where we fine tune because we know we're not optimal. In this case, both of them are basically optimal from 0 episodes. So having learned those base skills, we go off and we learn how to collect coffee and how to collect mail and how to visit the office. And then having done that, we can solve these tasks zero shot. And a final point is that this has a lot of applications to safe RL because of that negation operator specifically. So let's say we learn skills that say, visit this button over here, visit this hazard region, visit the cylinder. Well, then we can say things like navigate to a button and then go to a cylinder, and that works. Then we can say navigate to a button and then a cylinder, but never enter this hazard region, and then it will avoid the hazard region. And we can do navigate to a hazard and then a cylinder, and then finally, so this will go to a hazard, then the cylinder, and then to another cylinder, but avoid the hazard on the second time round. So you can imagine applications to safe RL there. Okay, so just to wrap up everything, in terms of future work, the things we're looking at are very much on the base skills. So in order for all of this to work, we still have to be able to learn those goal-oriented value functions, which are still, we're still using model-free reinforcement learning algorithms, all the things that are out there, PPO, SAC, whatever the case, they're still very sample inefficient. So improvements on that, which is great because other people are working on improvements to RL algorithms. We can just incorporate those into our framework. Things like, hindsight experience replay, better exploration, all the rest. The quicker we can learn those skills, the more likely it is we can actually do learning on a real robot. And once we can do learning on a real robot, then we start having the ability to actually solve these tasks in the real world. There's still the question of language. As I mentioned, very hard to train these things end to end, just from an engineering point of view. So there's work to be done there. And as John mentioned, the ability, once we start talking about temporal composition, and now we're talking about this and then that, but never this, language becomes much more complicated. And so translating from natural language to LTL, is an exciting area to focus on. I think, again, large language models are probably the way to go, just because there is a lot of data out there on the internet, a lot of examples of LTL from, college courses and all the rest of that. And so my feeling is large language models would have would have a lot of that in its training data and probably be a good fit. And then the final thing which is a bit more speculative, is to think about is, if we think about like the hierarchy, like Chomsky's hierarchy or hierarchy of like formal languages, we've looked at just simple, expression, Boolean expressions. We have finite state machines in these reward machines, but we could think about, okay, well, instead of giving the agent a reward machine, which is a finite state machine, what if it had like a Turing machine that had a tape and it could count and do all these things? Okay, if we had that, then could we apply the same kinds of ideas to solve tasks like that? Like, first of all, what tasks could we then specify if we had like a reward Turing machine? Is that a useful thing to have? And if it is, how could we incorporate it into this to kind of solve new tasks without further learning? Okay, so I think let me stop there. I just want to say thank you to all the students who have contributed in one way or another to this research project. Cool, thank you.
Wonderful, thank you so much, Steve. That was absolutely fascinating.
Yes, sir.
So I have a quick question. I don't know how concrete this question is.
Yes.
So I can imagine, sort of using natural language, you might want to specify something in less detail than you did there about, exactly the order. Mm-hmm. And you would like the agent essentially to figure out, it's sort of like an RL problem in and of itself. What's the way to decompose this simple, a simple instruction into a set of, basic movements, whatever, and then you want to go out and be able to learn those independently to be able to compose them. Is there any thought on that?
That's a super interesting question. I think that also. So I don't have a direct answer. I think very interesting question. I think it's also interesting because so far, kind of all the things we've spoken about are like straight line plans almost. Like, you do this, then you do this, then you do this. But you can imagine in a lot of cases, there are like, you have like these kind of task networks where it's not just a chain. You can do like this task, and the ordering doesn't matter, but just make sure that these two things happen at some point. And maybe ordering matter, like do A and B in any order you want, but then do C as long as you've done both A and B. And if you're doing cooking, like put the thing in the oven, and then while that's happening, you can do this, and you can do two things in parallel. So I think there's a lot of interesting stuff in that space, certainly both from like a specification point of view, like can you go from natural language to like, a task network that describes the partial ordering over tasks that you need, not like a total ordering. Can you go from natural language to that, and then can you incorporate that into like, say, a reward machine framework or something like that the agent could use to plan over. So I think, super interesting question. I don't have a good answer for you, but I'll definitely give it some thought.
Cool, thank you. Asad.
Thanks, really fascinating talk. I know it's very close to time, but just a quick question. I just want, like, this is like really exactly where you want to be, where you're in a space where there's a lot of scope for future work, for solving fundamental problems. So I just wanted to know, the initial phase, if you go back to like when this project and all of this started, did it just come about from like between the people at the Rail Lab? You had years of experience with RLab, you identified these fundamental issues and decided to try out like how you could apply logic to learn compound tasks, and people weren't really doing this at that time. And like, I just want to know on that, like, how did this initially come about? And as you keep publishing in the space, what's the current state of like what other labs are doing in this space? Because it's very interesting to get to a point where you are, where there's a lot of scope to keep extending this work and keep making fundamental contributions.
Absolutely. Thanks, Asad. That's a super interesting question. If I had half an hour, I could do a whole other history on that. But basically, in short, the idea was initially when this all started, we were not thinking about this at all. What we were thinking about was something called linearly solvable MDPs. One of our guys was doing his PhD on that. The idea there is the Bellman equation. If you make certain assumptions, the Bellman equation loses the max operator, becomes a linear operator. When it becomes a linear operator, you can now do things like adding two value functions together, and you get a meaningful thing out at the end. But in order to do that, they had developed this whole other linearly solvable MDP thing, and it was very complicated, and it wasn't actually particularly useful. And then the guys saw a talk from a guy from Berkeley who basically showed that when you do entropy regularized reinforcement learning, the Bellman equation becomes linear. That wasn't the point of his talk, but he mentioned that as like a side thing. And then we thought, okay, well, if that gets us the same thing that this linearly solvable MDP is, let's just do that. Because that's just standard RL with a bit of extra stuff. Let's just do that. So we did that. We showed that you could recover this. And then we showed, oh, well, when you add those two things together, what you actually get is just like the OR. So we showed that like you get the semantic OR coming out of it. And then we showed, oh, well, how do you do the AND? You can't really, like, we took the average. And at the time, like, the average was the best thing to do. We averaged the value functions, and you kind of got the AND. And then we said, okay, well, that's enough for now. Future work will focus on that. And then after that, then we thought about, okay, why doesn't the AND work? Why does the OR work, but not the AND work? And then that led us to, like, when we thought about that, basically the kind of key realization was, let me just quickly go back. Was this sentence over here that says, was this intuition that says, like, the problem is when you solve tasks, you learn about like the best thing to do, and you don't learn about the other things. And if the intersection is actually one of the other tasks, then you're not going to have any knowledge about that. So like if you're collecting blue objects and the best thing to do is to go to this one, and then later on you find, oh, actually, when I do the intersection of two things, I actually want, say this one, but I've only ever learned to go to this one. I have no knowledge of how to get to this one. And so we realized we needed to do this kind of like goal-oriented thing where you have to learn about all the different goals you could achieve, because maybe when you do the intersection, it's actually not this one that you should be going to, it's this one you should be going to, or this one, or whatever the case is. And then from there, that kind of, generated this whole like framework of, okay, let's make that work. Okay, great, we can do ands and ors and nots. okay, what's missing? Okay, we need like next and thens and you know, ensuring something is never true. How do we achieve that? And kind of build from there.
Ahmed, you had a question there. He's written it in the chat. It says, using this method, is there a way to generalize the side effects? Oh, sorry, go on.
I'm in a bit of a noisy environment. Just type in the chat.
Okay, I can read it out. Using this method, is there a way to generalize the side effects that we would want to avoid? For example, in a real world example, if we had several types of decorations or other side effects to avoid, assuming that specifying every possible side effect would be too burdensome.
Okay, yeah, that's a tough one. Basically, what it comes down to is like how you specify those initial tasks that you solve. So in the reward machine framework, they have these ideas, all of these things like the coffee and the person and the decoration is a proposition, and that you can think of this as like an abstract state. So they say, okay, like, you know, being like collecting the coffee means like I've collected the coffee, that's an abstract state, and it refers to all states where I've collected the coffee. You know, there might be many coffees, but all states, then this proposition gets set to true. So if you have like different types of decorations or things, or more generally, like there are things that I don't want to achieve, then you could say, okay, like those are the bad things. And you could say there's like a proposition for something bad happening.
Mm-hmm.
And then you would say, oh, I want to do a thing and make sure that the bad thing doesn't happen. But that bad proposition abstracts all the like lower level, don't fall in the lava and don't get hit by a car and don't break the decorations, don't spill the coffee. And all of that is just the bad proposition. And then you just say, do the thing and don't let bad happen.
That's very cool.
So
you can you can sort of think about it hierarchically there.
Yeah, exactly. Yeah, which is exactly your answer there is exactly right.
Sure. And presumably thinking about this, so I think Sinjan is here, who thinks a lot about sort of causality. Presumably putting this within a causal framework would also be very interesting.
Yeah, absolutely. I think the two interesting things. So I think maybe on the like pure reinforcement learning side, and you know, more about causality. One is about like, you know, this is all given to the agent. These kind of abstract propositions are given to the agent, but you know, in RL we don't like to give things to the agent. So you know, can these be learned? Mm-hmm. Can this reward machine structure be learned from data? And a lot of that structure will come down to, you know, you could imagine this as like a structured learning problem. Mm-hmm. You know, if you say, oh, like I need to, you know, get the key to open the door, and I can only open the door when I have the key, and, you know, learning those dependencies would then say, oh, you want to open the door. Oh, it depends on the key. Okay, and then that sets like a sub goal. So you should go off and get the key and then open the door. And you can imagine like the causality, you know, that being an interesting way of incorporating that.
Amazing. Are there any other questions? Oh, Asad, yeah.
I might just ask a very quick question. Just apologies if it seems quite naive, but what were the, and I'm sure there'll be a lot of challenges that we face, but given that the theoretical framework was done previous, you worked on the theoretical framework, what challenges did you face when you attempted to go the sim to real route? Like, were there engineering challenges, or like where was the you know, was it a case of like applying it into the real world, see what it translates, see what issues you'll have, or like what challenges do you face when you try to apply this in the real world?
Okay, so when you go to real world, and the idea behind that paper for sim to real transfer in general is saying like we want to do all of like the high level thinking and planning in like an abstract sense, and also what we'd like to do is like learn about behaviors in like a simulated environment. So the idea was to say, let's build like a very rough simulator of a real robot, and then we'll learn all our things. And then, okay, the real world is now far more complicated than that rough simulator. So how can we make corrections? And basically all of that was like an engineering, but also algorithmic, but like, it was all about saying, oh, well, you know, I must go and walk through this door. Okay, now I'm going to go walk through the door. And then a lot of work goes into like error correction and things like, oh, I expected to have walked through the door and I haven't walked through the door. Okay, let me replan and do things like that. So very much we wanted to separate out the reinforcement learning and the planning into like a simulator and a very coarse simulator, and then say, okay, if we wanted to work in the real world now, we have to make that connection and do error correction and all of that. Ideally, in the best case, once we have really sample efficient base algorithms, we'd want to do all the learning on the robot. you know, 1,000 samples or whatever, and then it must learn all the things and then be done. And we don't have to do sim to real, but you know, that still will require more work on that front.
Awesome. Very good. If there are no other questions there, thank you so much again, Steve, for a really interesting talk.
Yes, and again, thanks for inviting me to talk. Had a great time.
Absolute pleasure. Very good. We'll talk to you soon, and thanks everybody for coming.
Yeah.
Yes. Bye for now. Bye-bye.